Let's look at one more example of a flux-type integral. In this example, let S be the portion of the cylinder x squared plus y squared equals 4, given the outward orientation, where by outward I mean pointing away from the z-axis, and I want to restrict z to being between 1 and 3. F is the vector field 2x, 2y, z squared, and I want us to find the double integral over S of f dot big ds. So first of all, let's get an idea of what the picture is. X squared plus y squared equals 4 is a cylinder of radius 2 centered along the z-axis. So here's the z-axis. And notice I want to restrict z so that it stays between 1 and 3. So this is a portion up here above the xy plane. So our first step is going to be to parameterize. So let me capture the vector field. I'll write it over here. F is equal to 2x, 2y, z squared. And let me write the equation, x squared plus y squared equals 4. And now we can erase this part. Well, since we're integrating over a cylinder, we're certainly going to use cylindrical coordinates. So we're going to think x equals r cosine theta, y equals r sine theta, and z equals z. And we substitute that into the equation for the cylinder. X squared plus y squared equals 4. Well, in cylindrical coordinates, x squared plus y squared is r squared. So we get r equals 2, which is the radius of this cylinder. Substituting that r back in over here, we get x equals 2 cosine theta. Y is 2 sine theta. And z is simply equal to z. If I want to write that in phi form, then phi of theta and z, those are my two parameters, is equal to 2 cosine theta, 2 sine theta, and z. As far as the bounds go, since I want to go all the way around, theta is going to go from 0 to 2 pi. And we were given the restriction that z stays between 1 and 3. So later when we set up our bounds for the integral, those will be our bounds. Step 2 is going to be to find a formula for ds. Now remember, the formula for ds is plus or minus d phi d theta crossed with d phi dz d theta dz. And we'll choose the plus or minus so that I get that outward orientation. So in pictures, I want a vector on the surface to be pointing away from the z-axis, not inward. So let's calculate those two partial derivatives. d phi d theta is equal to negative 2 sine theta, comma, 2 cosine theta, comma, 0. And d phi dz is 0, 0, 1. So when I take the cross product of those, let's imagine that I, j, k appear. I get 2 cosine theta comma 2 sine theta and then 0. Now, we're not too surprised that the z component of the cross product is equal to 0, because notice that any normal vector to the cylinder is going to be parallel to the xy plane. So that means that its z component is 0. If it were pointing this way, upward, it would have a positive z component. This would be a negative z component, but since it's horizontal, the z component is 0. So that's not going to help us choose the plus or minus. So instead, let's pick a particular point on the cylinder and calculate what this vector is at that point. So for example, if I trace up above the x-axis, let's say this point right here above the x-axis. That point is going to have a z component of 1, because it's at the bottom of the cylinder, and the theta is going to equal 0, because remember, theta measures the angle away from the positive x-axis. So let's take theta equal to 0 and z equal to 1 and plug it into this formula. That would give me 2 cosine of 0, 2 sine of 0, and 0, which is 2, 0, 0. 2, 0, 0 is a vector of length 2 parallel to the positive x-axis. So notice that this vector is already pointing in the correct direction. So I do not need to put a minus sign in front of this cross product. So let's see, where am I going to capture that? I can just write it up here. What we figured out is that vector ds is equal to positive the cross product, which is 2 cosine theta, 2 sine theta, and 0 d theta dz. Step 3 is going to be to plug in, set up the bounds, and integrate. So we're trying to find the double integral over s of f dotted with ds. And remember, f is 2x, 2y, and z squared. So let's substitute in. From our parameterization, we know that x is 2 cosine theta, so I'll plug that in right here. I get 4 cosine theta. Y is 2 sine theta, so I'll plug that in here, getting 4 sine theta. And z squared is just going to be z squared. So remember, when you're substituting into f, pull the values out of the parameterization. So you can read those either here or here. And then we dot that with big vector ds, which is 2 cosine theta, 2 sine theta, and 0 d theta dz. And I don't need this part anymore, so I'll clear it. Our bounds on z are from 1 to 3, and on theta are from 0 to 2 pi. So let's carry out the dot product and then do the integral. With the dot product, I multiply corresponding components, so I have 8 cosine squared theta plus 8 sine squared theta plus 0 d theta dz. Oh, wow, this one's a nice one. So this is the integral from 1 to 3, integral 0 to 2 pi of 8 d theta dz. So I could break this up as 8 times the integral from 1 to 3 of dz times the integral from 0 to 2 pi d theta, which will be 8 times z taken from 1 to 3 times theta taken from 0 to 2 pi, which is 8 times 3 minus 1 times 2 pi, which is 8 times 2 is 16 times 2 is 32 times pi.